we have two main units to go. This one on electrochem and then nuclear. We'll take about 2 weeks on each of them, and that will finish our year. Much of what you might remember from honors chemistry, you'll find repeated in this chapter. The big difference will be towards the end when we tie electrochemistry into both thermodynamics and equilibrium. You might remember that metals have different activities. Some metals want to lose electrons more than others. We say that those are the more active metals. And you can have an activity series of metals with your very active metals, such as magnesium and zinc towards the top, and less active metals in the middle like copper and lead, and very non-reactive metals towards the bottom like gold and silver. Then, of course, you could throw in the alkali earth metals, which are extraordinarily reactive. They even react in water. And you could develop this activity series. Well, just like different metals want to lose electrons more than others, you could say that different metals want to gain electrons more than others. In other words, they have a higher electronegativity. So anytime you have two different metals that are in contact, meaning, that there's an electrolyte between them, or that they're touching, the electrons will go from the more active metal, the one that wants to lose electrons the most, to the one with the highest electronegativity in comparison to the other. For example, if you were to put silver wire into copper sulfate and copper wire into silver nitrate, in one you would get a reaction, in the other you would not. In the bottom of the page here, you can see that if you were to put a piece of copper wire into some silver nitrate, a chemical reaction would take place. Because the copper is more reactive than the silver is going to go from its silver ion in solution to pure silver, and the copper is going to go from its copper ions, the copper metal, to copper ions in solution. And of course, copper ions, copper 2 ions, are blue colored. And you get all this silver that corrodes or cakes out on top of the copper wire, some of which will fall to the bottom of the beaker. This, of course, is what we would call a redox reaction. Oxidation and reduction are taking place. Your silver is going from a +1 in solution to a 0 as pure silver. And so since it's going down the number line, it's being reduced by gaining electrons. And your copper is going from copper atoms, 0 oxidation number, if you remember them, to copper 2+ ions. It's going up the number line. It's becoming more oxidized, more positive because it's losing electrons. And you might remember the famous line, Leo says Ger. Leo, loss of electrons is oxidation. Ger, gaining of electrons is reduction. The net ionic equation, where you have the spectators canceled out, the nitrates canceled out, and where you show both a balancing of atoms and a balancing of charge, is highlighted now in blue. Notice that you would have a balanced net ionic equation without the number 2 in front of the silver ion and the silver atom. It would be balanced according to atoms, but it would not be balanced according to electrical charge. These kinds of batteries, where we intentionally put two different metals into a material with a conducting material between them, are called voltaic cells or galvanic cells. We should also say that you can have unwanted voltaic or galvanic cells when you have an electrochemical reaction going on, redox going on, that you don't want. That would be an example of corrosion and rusting. And we have that in our bridges all over Missouri and all over the country for that matter. Now, voltaic cells are named after a rather interesting gentleman, Mr. Volta, whose actual name is Alessandro Giuseppe Antonio Anastasio Volta. From his last name, we get the word volt, which is our unit of electrical potential energy per charge, work per charge. You can see when he lived during the time of the American Revolution. And interestingly enough, he was a Catholic and a Christian, rather devout, but not necessarily practicing all of the trappings of the Roman Catholic faith. And for that, he was accused during the course of his life of not being a good Catholic, being there in Italy and near Rome. And towards the end of his life, he actually wrote a response to these accusations in which he cited and referred to supernatural grace in his life, a very Protestant and Reformed concept, and also quoted from Romans chapter 1, "For I am not ashamed of the gospel." He was just rather quiet about his faith, and he busied himself with his science. Not only is he considered the inventor of the electric battery, he also discovered methane, I think from reading a paper by Benjamin Franklin. I might not remember that correctly. He was also greatly admired by Napoleon. One of his colleagues early on was Luigi Galvani, and so sometimes our voltaic cells are called galvanic cells. In any case, a voltaic cell is a cell that provides or produces an electrical push to a charge, and if we put something in the way of that charge with its potential energy from the electrochemical voltaic cell can do work. It can light up a light bulb, run your calculator, your smartphone, all kinds of ways that we use voltaic cells because we now have all kinds of different voltaic cells. If I was in class, I would do a demonstration with a wet piece of paper towel in between a copper and a nickel, two different metals, conducting material between them, and we get electrical energy. You can also make these at home. All you need are two different kinds of metals and stick them into a lemon or an apple or a potato, and you've got yourself a voltaic cell. Hook the external circuit up to some device, and you can do work on that device. Now, another kind of electrochemical cell is summarized by the word electrolysis, where we use electricity to accomplish work. So there are two kinds of electrochemical cells. In one kind, we use our chemical energy to get electrical energy. We call that a voltaic cell or battery. In the other kind of electrochemical cell, we use our electricity to get some kind of chemical energy or work done. And electrolysis is an example of that. We call that an electrolytic cell. Electrolytic cells are the opposite of voltaic cells. In either case, they are all electrochemical reactions involving oxidation reduction, the transfer of electrons. We can draw a couple of observations with these bullet points here. You can't have one without the other. If you have one reactant that's being oxidized, rest assured there's got to be another one that's being reduced. You can't have something losing electrons without having something else gaining electrons. The amount of electrons gained and lost must equal each other. Redox must be balanced. The thing that is oxidized is the reducing agent, and the thing that is reduced is the oxidizing agent. Now, that's not entirely accurate. It's an easy thing to remember, but you have to remember that the agent is actually the entire species that contains the metal that is being oxidized or reduced, or I should say the element that is being oxidized or reduced. That's very important to remember. Some of you will get tripped up on that in the test. The agent is the entire species that contains the element that is being oxidized or reduced. And we'll see some examples a little bit later on. At the very bottom of the page, you see a discussion of balancing oxidation-reduction equations. One way to do that is with the half reaction method. And that's, by half reaction, we mean you balance half of the reaction that involves just oxidation, and then you balance the other half of the overall reaction that involves just reduction. Once you've balanced your two half reactions independently, then you put them together, making sure that the total number of electrons lost in oxidation equals the total number of electrons gained in reduction. For example, back to our example with silver and copper. You can see the half reaction for silver, where silver is gaining electrons. So you put the electrons on the left. The gaining of electrons is reduction. And you can see copper is losing electrons. You put the lost electrons on the right side. Losing electrons, of course, is called oxidation. But you'll notice that these two half reactions do not have balanced electrons. That means that the silver electron reaction, the silver half reaction, the reduction half reaction, is going to have to be doubled. Multiply everything by 2. Now you have 2 electrons being gained to go with the 2 electrons being lost. And then your net ionic equation is when you add these two half reactions together, canceling out the electrons. Lots of redox reactions can be balanced this way, especially when the battery, the electrochemical voltaic cell, is nothing but 2 different metals. Here's an example involving copper and aluminum. And when we come to the bottom line, the very bottom of the page, the half reaction for aluminum involves 3 electrons. The half reaction for copper involves 2 electrons. So you multiply one half reaction, the reduction one, by 3, and the oxidation half reaction by 2 to get 6 electrons gained or lost in order to get your balanced equation. Now we come to the part of the chapter where the reactions that we might want to balance in a redox reaction are much more difficult. And they're not going to be balanced according to memorizing patterns like single replacement and decomposition and so forth. And they're not going to be easily balanced just by kind of looking at them and inspecting them in a little trial and error. You need a more sophisticated way to balance them. And the reason they're so hard, it's not always easy to see how many electrons are gained or lost. And you often have oxygen or some other element like it in multiple places. And as a result, you begin to realize that every time you try to balance it, getting the coefficient to be correct for one of your species, it messes it up for another species that might have the same element. Not only that, but we have to balance charge of the particles, and we might be in an acidic or basic environment, which means we would have some hydrogen ions or some hydroxide ions that we could use in writing our balanced equation. Now, I have covered this in a separate screencast, which I think you'll find very helpful, the way that I've done it with this technique of screencasting. And so I'm not going to do that here. I'm going to skip through a bunch of these pages. But this is the method of using the half reaction for balancing complicated redox reactions, where you are balancing out the electrons, you're balancing out the charges, you're adding hydrogen ions if you have an acidic solution, and hydroxides if you have a basic solution, and finally balancing out with water. I think the technique that I use, that I've invented for myself, I find it easier than this. In my technique, you balance 5 different things, potentially, after you assign the oxidation numbers, and you have to look at the separate screencast to remind yourself how I do it. All right, simple voltaic cells. A simple voltaic cell often is just made out of 2 different kinds of metals with an electrolyte between them. And the key in understanding and designing a voltaic cell is to know which metal wants to lose electrons the most. Or another way to put it, which metal wants to gain the electrons the most, has the highest electronegativity. And for that, we'll be looking at a chart. But let's get some terminology out of the way. The terminology that you need to understand, you might remember from first year chemistry, is the salt bridge, the anode, the cathode, the positive electrode, and the negative electrode. And these vocabulary terms are important for both electrochemical cells that are voltaic and the electrochemical cells that are electrolytic. The electrochemical voltaic cells give you electricity, thanks to the chemistry, and the electrolytic cells give you chemistry and work, thanks to electricity. Indeed, you could use a voltaic cell to power your electrolytic cell. Now, one of the keys to understanding the vocabulary is that the anode is always the metal where oxidation takes place. And the easiest way that I find to remember this is that both the word anode and oxidation begin with a vowel. A and O are vowels in the English language. And cathode and reduction do not begin with a vowel. Regardless of the electrochemical cell, oxidation is always at the anode, reduction is always at the cathode. The only thing that changes is which electrode is positive and which is negative. They are different between electrochemical voltaic cells and your electrochemical electrolytic cells. Now here's a diagram of one, and on a test, you might remember this from first year chemistry, I selected 2 metals and told you on the test to design a voltaic cell, to put the salt bridge in, tell me what solutions that you would use for electrolytes, tell me which way the electrons were going to go, calculate the voltage for me, tell me which electrode has oxidation, which electrode has reduction, tell me which is the positive and which is the negative, which is the cathode and which is the anode. It was worth like 12 points on that test. You might find something very similar in the not-so-distant future. Now, in this particular diagram, you'll notice that we have an electrochemical voltaic cell made out of copper and silver as my electrodes. And if you didn't have a chart, you should know by common sense now that copper is much more reactive than silver, silver being relatively inert, which means copper wants to lose its electrons more than silver does. So if copper is going to lose electrons, that's Leo. Loss of electrons is oxidation. And if this is oxidation, then it is the anode. And also because it wants to lose electrons, you can think of it as being the source of electrons. So therefore, it is the negative electrode. And in order to keep your copper electrode from corroding, you would want to use a soluble copper salt, like copper sulfate, copper chloride, or in this case, copper nitrate. On the other side, the right side of your picture, is our silver electrode. By comparison to copper, it is more inert, So by comparison to copper, it's going to gain electrons. It's more electronegative. Gaining of electrons, GER, is reduction. Reduction takes place at the cathode. It's attracting the electrons, so to speak, and so it's the positive electrode. Now, you have to have a complete circuit, and that's where the salt bridge comes in. A salt bridge can be one of many different things. It can be a porous barrier between two solutions that will allow the charge to get through. It can be a wet piece of paper towel that's draped over the sides. You might remember in the lab that you did in first year chemistry, it was a wet paper towel with salt solution soaked in the middle. In this case, we have a U-tube upside down. And remember, chemists invented the U-tube first. And you have a solution that's an electrolyte inside. You want some non-reactive metals, such as sodium or potassium, as your metal ions. And it needs to be a conducting solution. We usually use nitrates. And to keep that solution from escaping the upside down U-tube, we have a porous plug. It could be a cotton swab in there. You could even make a gelatin, out of salt, and that could be your salt bridge. Now, if you look at the very bottom of the page, you'll notice this little nomenclature here where they have a vertical line in between the electrode and the solution that the electrode is in. You're going to see that again also. You'll also notice they talk about 1 molar solutions. 1 molar solutions you're going to see are what we call the standard molarity when we come up with our standardized way of finding the voltage. And we use a standard temperature of 25 degrees Celsius. Here's another way to draw a voltaic cell. This time my salt bridge is a barrier between the two solutions, but it's a permeable or porous barrier that can allow ions through to complete the charge. And in chemistry, we usually talk about the movement of the negative charge, which in this case in the circuit would be clockwise. In physics, we often talk about the movement of the positive charge by convention. Please note that instead of a voltmeter, you could have a light bulb, a buzzer, your calculator, your smartphone, something that needs a battery. Though I strongly encourage you not to try to use an electrochemical cell to charge a device, that costs over $100. Here's another example, but this time we're using iron and copper. And you might not know, well, which electrode, iron or copper, wants to lose electrons the most? And here's where you'd have to go to a chart. You would need an activity series for metals, or you would need a chart, which we'll get to in a little bit later, called the half reduction potential chart. And you would see that iron wants to lose electrons more than copper according to the chart. And so in this case, the copper becomes the cathode instead of the anode like it was compared to silver. And you would have to be able to calculate what that voltage is. So again, you would need a chart for figuring out that voltage. And that chart is in the middle of this chapter. Often it's also at the end of the book. And on a big test, you would be given a table, and you'd have to look up each metal. Now, here's a little hint, because this is a mistake people make on the upcoming AP chemistry test. You will find that in your half reduction potential chart, there is a half reaction for the copper 2+ ion and a half reaction for the copper 1+ ion. Make sure you pick the right one, or you'll get the wrong voltage and you'll get everything wrong. Now, a lot of times, we're going to use an inert electrode instead of a conducting electrode. And the chemical redox reaction will take place in the vicinity that surrounds the inert electrode. And on your AP college test, you should know what we mean by inert. An inert metal would be a metal that, for all intents and purposes, doesn't want to gain or lose electrons. You could use silver, maybe. You could use gold, but they would be very expensive. A cheap one would be to use carbon or graphite, like your typical D cell or C cell battery might. But a lot of times we will use platinum as our inert electrode. Platinum electrodes are kind of expensive, but once you have them, they're going to last a long time if you take care of them. Now, in order to come up with the voltage, the potential difference for every single possible thing that we can conceive of as being an electrode, we need to have a basis of comparison. To use an example from physics, if we have sea level as our standard elevation, we could say that anything at sea level has zero potential energy. And anything that I begin to lift above sea level is going to have more and more potential energy as I lift it higher and higher. Hopefully you remember that potential energy equals the mass of the object you're lifting times the acceleration due to gravity at that point times the height. So your potential energy is directly proportional to the height. Now, by the same token, at sea level, if you were to move something below sea level, in a sense, you have a negative potential energy. Well, in this case, we have the same idea. If we pick a sea level, some things are going to be positive potential energy per charge. That's what a volt is. Voltage is not potential energy. Voltage is potential energy per charge. Some things will have a positive potential with respect to this standard electrode, and others would have a negative potential with respect to this standard electrode. And we have chosen hydrogen as a standard electrode. We call it the standard hydrogen electrode, SHE, S-H-E. And so in order to have a standard hydrogen electrode, hydrogen obviously isn't solid. So if you look at the bottom of the page, we have an inert platinum electrode around which hydrogen is going to be forming hydrogen ions into hydrogen gas. And that's going to be going on at one of the electrodes. So in this case, the electrode is not what's being redoxed, but it's facilitating the region around it where redox is going to be taking place. And if you look towards the middle of the page, you'll notice that your standard hydrogen electrode, in that vicinity, you can either have electrons being gained, reduction, or on the right side, electrons being lost, which would be oxidation. And of course, the left one, where it's being reduced, you would get bubbles of hydrogen gas forming, if that was the reaction going on at that place. In the right side, you would have the production of hydrogen ions, and so you would have an acidic solution being formed. Now, in order to show you a kind of nomenclature for showing an entire redox reaction for a voltaic cell, notice how we do it. We put the stuff on the anode on the left. We put the stuff of the cathode on the right. The electrons are going from the left to the right. Just like we read in English, we read from the left to the right. And so you have your copper turning into copper ions at the anode in a 1 molar solution, and you have your silver ions becoming silver at the other side in a 1 molar solution of silver nitrate. This would describe, if you were typing it out on a computer in a journal article for other people around the world, the kind of voltaic cell that you would be discussing. Let's talk a little bit about a few commercial voltaic cells. We won't go into too much detail, and nor will the AP, but it might have a multiple choice question or two. So commercial voltaic cells, ones that you would buy at the store, one that you would routinely use. Some of them are called primary batteries. Remember, the word battery is an everyday word for a voltaic cell. In science, technically a battery is a combination of voltaic cells. But primary batteries can't be recharged. Secondary batteries are rechargeable, like the car battery. Primary batteries are sometimes called dry cells because there's no solution, but there is a moist paste. Alkaline batteries, which are a little more expensive and they last longer, alkaline batteries, of course, are going to be basic. There's going to be something that is a hydroxide that's part of the material of the battery. And they last about 50% longer than the dry cells can. You'll notice that one of your electrodes is an inert carbon cathode running down the center of the battery. The other electrode is usually zinc. If you were to peel the paper off a battery, you would have a zinc cup with a piece of steel at the bottom and a piece of steel with a little knob on it at the top, connected to the graphite electrode. You'd have some potassium hydroxide in an alkaline battery. A lead storage battery is what we would call the battery in your car. Alternating plates of lead with battery acid, sulfuric acid, is the solution that they're immersed in. And an automobile battery only produces 12 volts of energy, but it's a huge deluge of current, huge amount of water. Instead of a little trickle of water, it's like a huge Niagara Falls of water, lots and lots of current, called the cranking amps to start the starter motor, which will start your engine of your car time and time and time again. A high voltage battery, like higher, might have lots of volts, but very, very little current. You need to know the difference, and that is explained in one of the handouts. We also have nickel-cadmium batteries, and obviously you can tell what the two electrodes happen to be. You want to be careful about disposing of them because of the environmental hazards. They produce a nice, steady, constant voltage, kind of expensive. You can have metal hydride batteries. We haven't talked much about metal hydrides, but in a metal hydride, the metal is the positive ion, and hydrogen becomes your negative ion. Most of the time you think of hydrogen as being +1. Well, in a hydride, metal is a -1. Lithium batteries are really popular right now, and they're used to power lots and lots of our favorite electronic devices. And this is a huge field of research, and there are Nobel Prizes waiting to be won in this area. And one of these days we'll have batteries that will last for weeks, if not months. And of course, we want them to be lightweight. We want them not to be expensive. We want them to be something that's not dangerous in the environment. All of those kinds of things. You can also have a fuel cell. In a fuel cell, which we might use in a device in outer space or for an electric car, is a way of getting electricity from simple hydrogen gas and oxygen gas. Now, you would get your hydrogen gas and your oxygen gas through electrolysis of water in the first place. And then those tanks of hydrogen gas and oxygen gas, you would feed those two gases into this chamber, this fuel cell, and when the gas was met, it would produce water, but in the process of exchanging electrons, you'd get your electrical potential that could do work for you. And of course, we don't have too much time to spend on that. Now, calculating the voltage. The standard hydrogen electrode is our basis of comparison. And we want to calculate the potential energy per charge based upon calling the standard hydrogen electrode 0 or 0 volts. An old-fashioned term for this energy per charge is the electromotive force, abbreviated EMF. Now, first of all, volts and forces are not the same thing. Forces are measured in newtons, and an electromotive force is not a force, and it's not measured in newtons. An electromotive force is work per charge, joule per coulomb. But EMF is kind of like the oomph, the push of that charge out the battery through an external circuit where it can do work, like light up a light bulb or run your calculator. And we already mentioned using the standard hydrogen electrode. And we already mentioned that we talked about the elements being in their standard states, your molarity being 1 molar. You have about 1 atmosphere of pressure, 1 bar. You have 25 degrees Celsius as your standard temperature. And what this means is that you can change the voltage of a battery by changing the conditions. You have your standard voltage, but you can get more or less by changing these conditions. Something that we did not do in first year chemistry, but when we start talking about equilibrium, we can do that here. Here's the standard hydrogen electrode. And we compare everything to the standard hydrogen electrode. Then we can begin to develop a table showing you a basis for comparing the voltages. You have your standard hydrogen electrode in the middle, and some have a negative voltage by comparison. Some have a positive voltage by comparison. Now, you can make a battery out of any 2 metals in this chart. If we were going to make a battery out of 2 metals, for example, iron and silver, they both happen to have a positive voltage. But you could make a battery out of iron and silver, where iron has a negative half cell voltage, and silver's is positive by comparison. And you could make a battery out of, say, aluminum and zinc, where in this reduction potential table, they're both negative. Now, how do we do that? And the answer is, how do we calculate the voltage? The answer is, let's remember what the negative and positive sign means. A negative voltage means non-spontaneous compared to SHE, standard hydrogen electrode. Something that is below sea level will not spontaneously fall upwards to get to sea level. However, something that is above sea level, if it can, will spontaneously fall back down to the ground, to sea level. Positive voltage means spontaneous. Negative voltage means non-spontaneous. The negative voltage will never happen by itself as written because it's non-spontaneous. The positive voltages can all happen as written, spontaneously. But since we have 2 different metals, the one that is most negative by comparison, in other words, the one that's farthest down the number line, is the one that is least spontaneous. So that's the one that you're going to reverse. The one that's least spontaneous can't happen the way that it's written, so that's the one you reverse. If we were comparing, for example, iron and silver, the one that is least spontaneous is silver, 0.799 volts, compared to the iron. So that's the one that you're going to reverse. And that means you reverse the sign on the voltage. By the same token, you might want to make a battery between, let's say, copper and iron here. And the one that is least spontaneous or most negative is the iron, negative 0.44. So that's the one that you would reverse. And so you would reverse its sign. Or you could make a battery, let's say, out of aluminum and zinc. There's aluminum, there's zinc. The one that's least spontaneous is the one that's most negative, so that's the one that you reverse. And one way then, when you go to calculate your overall voltage, see the little zero, the degrees symbol for the capital E, which is another way of talking about the voltage or electromotive force. We usually use the letter E for the battery itself and the letter V, like in the word volt, for the different parts of the circuit that the battery might be operating. But you take your voltage of your cathode, and the cathode is where reduction is taking place, where you're gaining electrons, and you subtract the voltage at the anode. And so now we come to our table of standard reduction potentials, which can get very, very, very long. And here's a small table. Please keep in mind that some books, or maybe some tests, might start with the negative and go down to the positive volt. This one goes from the positive to the negative. So how would I calculate the value of a zinc copper battery? Well, here's my zinc down there, okay? And I'm looking for the copper 2. And there it is. There's copper 2. You'll notice that this one has a positive 0.37. This one has a negative 0.763. How would I calculate their voltage? Well, the zinc electrode has the most negative voltage. So it is non-spontaneous as written. So therefore, I would reverse that half reaction and show it losing electrons instead of gaining. So zinc will be losing electrons, meaning it'll be oxidized, it'll be the anode, and it'll be a positive 0.763 volts, which when I add it to the 0.337 volts gives me 1.10 volts for a zinc copper battery. So the way that I always calculate the voltage is I take the half reaction that is most negative and reverse it, and then add it to the other one, be it positive or negative. I take the one that is most negative and reverse it because as written, it's the least spontaneous, so compared to the other, it's not going to happen. So I reverse it, that reverses the sign, and then I add it to the other one. And that's how I calculate those voltages. And I'm going to stop right there. It's been long enough, and we'll pick up in lesson 2.